In this video, we will analyze an inclined plane. I will begin here with a picture of an inclined plane. This inclined plane is inclined at an angle alpha, which is relative to the horizontal. And here we have a box with mass m on the inclined plane. I will present to you three ideal cases. Case 1 will be no friction. But before we proceed with case 1, we would like to choose a coordinate system. Our coordinate system will consist of the following. Up the ramp will be our positive x-axis, and perpendicular to the ramp will be our y-axis. Okay? So now we will proceed with representing the force vectors of all the forces that are acting on this box. For example, we have the gravitational force that is being exerted to the box by the Earth and is originating at the center of gravity with sense downward or towards the center of the Earth with magnitude mg, or mass times acceleration due to gravity. We also have the normal force. This force exists when two surfaces are in contact, and the normal force is always going to be perpendicular to the surface is in contact with. So here, let's draw the normal force. This is the normal force. We will designate it N for normal. Now that we have these two forces, we said that case 1, there is no friction. Before we proceed, I would like to tell you the whole point of choosing a coordinate system is to, again, decompose this force and any other force into their x and y components. In this case, the only force we need to decompose is the weight of the box itself. So we will proceed by drawing two vectors, which are the components of the weight, and the weight has a component this way, perpendicular to the plane, and we have a component parallel to the plane. The sum of these two vectors will equal the overall vector mg. Again, these vectors are not to scale in magnitude. The important thing is to note that this magnitude mg is being decomposed into these two components. The direction is important for our decomposition of this vector. If you remember from similar triangles, this angle alpha is the same as this angle alpha. Now we can proceed with decomposing these forces. We will decompose these forces right here. So we know we have the component of weight, parallel and perpendicular. The parallel component will be given by the weight mg in the x direction. Now, this is the parallel component, which is parallel to the plane, which is our x-axis. N is given by multiplying the magnitude mg, which is the hypotenuse of this triangle, times the sine of alpha. This will give us the projection of this magnitude, which is opposite to alpha. So we will multiply mg times the sine of alpha. Namely, the component of weight, the y direction, will be given by multiplying the magnitude mg, or the hypotenuse of this triangle, by the cosine of alpha. It will give us the projection of this magnitude adjacent to the angle. And it's given by mg cosine of alpha. We will implement now Newton's first law of motion in the y direction. The reason is why is Newton's first law of motion is because there is no acceleration in the y direction. This means this box will have no tendency to accelerate up. It will not fly up or sink down the inclined plane. So our equations tell us that the sum of the forces in the y direction is equal to, well, we have the normal force, which is positive, and we have the component of weight, which is perpendicular to the plane, or the y component of the weight, which is given by mg cosine alpha, and is negative because its sense is downward relative to the coordinate axis that we have chosen. Minus mg cosine of alpha. Newton's first law, the sum of the forces is equal to 0 because the body will either remain at rest or in uniform motion. In this case, this body is not in uniform motion, so it will remain at rest. Okay? Solving algebraically for the normal force, adding mg cosine alpha to both sides, we get that n, the normal force, is given by mg cosine alpha. The normal force will always be mg cosine alpha when we have this type of situation. If you can think of it intuitively, this angle is inclined to an angle alpha relative to the horizontal. So let's say we decrease this angle, and we keep on decreasing and decreasing until the angle alpha is 0. It's still inclined, but the angle is 0. We're going to put the angle 0 here, evaluate the normal force at 0. The normal force will be given by m, the mass, multiplied by the acceleration due to gravity g, multiplied by the cosine of 0, which is 1. Cosine of 0 is 1, multiply mg is the normal force. So if you can remember that, any body resting on a flat surface, the normal force is given by the weight of that body. And of course, you can see how this works out mathematically by just evaluating the normal force when the incline is 0 degrees. So now we will present case 1, which is no friction. I will present here now case 1. Case 1. You have case 1 here. No friction. We have no friction. This is case 1. So now what we will do is, in the x direction, we will implement Newton's second law so we can find out what is the tendency of the block with mass m. So in the y direction, I will write again here the sum of the forces in the y direction because there is no acceleration in the y direction, and minus mg cosine alpha is equal to 0. This is Newton's first law in the y direction. Now in the x direction, the sum of the forces in the x direction. Now we will use Newton's second law. We will add and figure out the net force, set it equal to mass times acceleration, and solve algebraically for the acceleration. Well, if we think of forces, this component of weight is acting down the negative direction that we have chosen relative to our coordinate axis. So the component of weight is a force acting on this mass, and is of course given by the parallel component of the weight. When we do that, we will obtain that we have a negative minus, we have minus mg sine alpha. Minus mg sine alpha. Okay? This is a force acting parallel to the plane. And since this is the only force, this is the net force. So the net force, by Newton's second law, we're going to set it equal to mass times acceleration. Solving algebraically for the acceleration A, we obtain that A is equal to, dividing both sides of the equation by m, we get negative g sine alpha. This means the tendency or the direction of the net force acting on this block right here is down the inclined plane or towards the negative direction. And if it will accelerate, in this case it will, because there is no friction, it will accelerate down the inclined plane with acceleration A and magnitude g sine alpha. So if there's no friction between these two, we will have an acceleration of negative g sine alpha. So now let's proceed with case 2. So in case 2, what we have here is friction. Case 2, we have friction. And I'm going to put here in parentheses static and kinetic. Static and kinetic friction. Okay? Let me write it right here. There you go. Static and kinetic. This is case 2. Now, if we had friction, we have, for example, static friction, which is given by Fs, and the maximum static frictional force is given by multiplying the coefficient of static friction times the normal force. But if you can remember here, the normal force is mg cosine alpha. So we will substitute that right here for the normal force. And we will get that mu sub s times mg cosine alpha is the maximum static frictional force. This means the net force that is acting on this body, M, should be greater in magnitude than the maximum static frictional force. Let me write that and illustrate that for you mathematically. So mathematically, we know that the net force, we have the net force is negative mg sine alpha minus mg sine alpha minus mg sine alpha, okay? Must be greater in magnitude than the maximum static frictional force, mu s mg cosine alpha, okay? The magnitude must be greater than mu s mg cosine alpha. After the magnitude of the net force is greater than mu s mg cosine alpha, or the maximum static frictional force, the body will then accelerate at a rate a, which is what we will find out right now. Now that we have reached our critical value, assuming that the net force minus mg sine alpha, or this net force minus mg sine alpha, is greater than the maximum static frictional force, we will now introduce kinetic friction. The reason is kinetic because now the body is in motion, and kinetic friction appears when the body is in motion. The net force direction is negative down the ramp. Kinetic frictional force will be opposite to the net force. So the net force is pointing down the ramp. We have kinetic frictional force up the ramp. So this is the only force that we will add in our x direction. So our sum of the forces in the x direction, we have x is equal to minus mg sine alpha, and kinetic friction is positive because it's pointing up the ramp and is given not by mu sub s, now is by mu sub k times the normal force, or mg cosine alpha, plus mu sub k, which is going to be the coefficient of kinetic friction, times mg cosine alpha, equals, of course, mass times acceleration. Now, we will solve algebraically for a, the acceleration a. We will divide both sides of the equation by m. So we have that a is equal to, on the left side we have a common factor of g, the acceleration due to gravity. I will pull it out. We will open a parentheses now, and we have mu sub k times the cosine of alpha, and here we have negative, g is already pulled out, m is already being divided out. We have sine alpha minus sine alpha. This is the acceleration if the maximum static frictional force has already been exceeded by the net force. Okay? I'm going to draw right here. I'm going to write for you right here. This is the net force. And this is Fs max. The magnitude of this force, F net, must be greater than Fs max. If this is true, kinetic friction will appear opposing the net force, and the acceleration will be now g times mu sub k cosine alpha minus sine alpha. Again, if we have no friction, mu sub k is 0, so we have 0 times cosine is 0, minus sine alpha is negative sine. And of course, as in case 1, if there is no friction, the acceleration will be negative g sine alpha, and it's the same thing we obtain here when mu sub k is equal to 0, or there is no friction. Another thing is, before we proceed, is that if this block were to move down the inclined plane at constant speed, and we wish to determine the coefficient of kinetic friction, how we will do that? Again, constant speed must remind you of Newton's first law. So we will implement now Newton's first law in the x direction. Sum of the forces in the x direction will equal to, well, we have the net force here, minus mg sine alpha. This is the net force because now we have friction, we have kinetic friction, plus mu sub k mg cosine alpha, and we're going to set that equal to 0. We're going to set that equal to 0. Now, this is equal to 0 because this is Newton's first law, and the body will now move in uniform motion unless acted upon an unbalanced force. There is no unbalanced force, this is the net force. Solving algebraically for the coefficient of kinetic friction, we obtain that mu sub k is equal to, well, if we add both sides of the equation mg sine alpha and divide by mg cosine alpha, we will get mg, okay, we will get mg sine alpha divided by mg cosine alpha. And as you can see here, the weight mg cancels, and we're left with the tangent of alpha. This means that if the block were to move down the inclined plane at constant speed, we can figure out experimentally the coefficient of kinetic friction by calculating what is alpha. But we have to know that the block is descending at a constant speed. Okay? So now we will know that case 3 is pretty much the same. Case 3, well, we already did case 3 indirectly, so let me explain it to you directly. Case 3 is descends at constant speed. This is case 3. Descends at constant speed. Okay? Case 3. Now that we know this descends at constant speed, we know, because we found out from the last equation, that the net force in the x direction is given by minus mg sine alpha plus mu sub k mg cosine alpha. We're going to set that equal to 0. This is Newton's first law. Now I will show you algebraically how we can get to tangent of alpha. I will add both sides of the equation. I will add what is plus mg sine alpha. Same thing with the other side of the equation. Mg sine alpha. Okay? Plus mg sine alpha. Plus mg sine alpha. On the left side, I'm going to be left with mu sub k mg cosine alpha is equal to what we already added, mg sine alpha. So this is where tangent of alpha comes from. We will divide here on both sides by mg cosine alpha. The reason we are operating on both sides is to keep the equation equal. On the left side, mg cosine alpha cancels with mg cosine alpha. On the right side, mg cancels with mg. And we're left what we had in case 2, which I explained indirectly. The coefficient of kinetic friction when the block descends at constant speed is given by sine over cosine, or the tangent of alpha. Okay, so to recap very quickly, we have case 1. But before case 1, I would like to show you the inclined plane itself. We have chosen a coordinate system. The positive x and positive y direction are perpendicular and parallel to the plane. The component of weight parallel to the plane, or the x component, is always given by mg sine alpha. mgy, or the component of weight in the y direction, is always given by mg cosine alpha. The normal force on an inclined plane is always given by mg cosine alpha. Case 1. In case 1, we have no friction. No friction. The sum of the forces in the y direction is 0. This is Newton's first law, because the body will not accelerate up or go through the ramp. In the x direction, we have the sum of the forces in the x direction. We know the net force is minus mg sine alpha. We're going to set that equal to mass times acceleration, the Newton's second law. We can solve here algebraically, and we get that a, the acceleration a, is negative g sine alpha. Negative is just indicating the direction of acceleration. G sine alpha is indicating the magnitude of that acceleration. Now we have case 2, when we introduce friction and static and kinetic friction. We have the maximum static frictional force, which is given by mu sub s times the normal force, or mu sub s times mg cosine of alpha. Alpha is relative to the horizontal, of course. We have the net force, which we calculated in case 1, the sum of the forces in the x direction. The net force is minus mg sine alpha, must be greater in magnitude than mu sub s mg cosine alpha, the maximum static frictional force. The signs are not important, that's why we took the absolute values, because we are only interested in the magnitude of those forces. After the net force has exceeded the maximum static frictional force, we have motion. Now the body begins to move. Now a new force appears, kinetic frictional force, and is given by mu sub k times the normal force. This kinetic frictional force will act opposite the direction of motion. Since we know the direction of motion is down the plane because of this negative sign, which is indicating the direction, we know kinetic frictional force will act up the plane, or towards the positive x direction that we have chosen relative to our coordinate system. The sum of these forces will now become the net force, and we're going to set that equal to mass times acceleration by Newton's second law. Algebraically, we can solve for the acceleration by dividing both sides of the equation by n, factoring out a g on the left side, and arranging the term from positive being first and the second one being negative. We get that if there is kinetic friction, the body will have acceleration a, which is equal to g times mu sub k cosine alpha minus sine alpha. And here I explain to you indirectly case 3, the sum of the forces. We have the net force plus kinetic frictional force. This is when the body will descend at constant speed. And at constant speed, we wish to determine, when we have that the block descends at constant speed, we wish to determine the coefficient of kinetic friction. And a way to do this is experimentally, by observing that the body will fall at constant speed. We have minus mg sine alpha, which is the net force, plus the kinetic frictional force that appears after the maximum static frictional force has been exceeded by the net force. We're going to set that equal to 0 by Newton's first law, because of course the forces must be balanced. They must be equal to 0 for the body to move in uniform or constant motion. We can add both sides mg sine alpha, which is the weight parallel to the plane. We get on the left side mu sub k mg cosine alpha, which is what we have here, and on the right side we have mg sine alpha, which is what we brought to the other side. Here we can cancel out this quantity. We're left with mu sub k on the left side. On the right side, mg cancels, and we're left with sine over cosine, which is a trigonometric identity for tangent of alpha. So mu sub k will be given by tangent of alpha, and these are all three cases when we have an inclined plane, no friction, kinetic and static friction, and the body descending at constant speed.